Damn, we need to start filming. Someone shoved my hand somewhere, damn it. Slacker Vishnya. Anger is about to hit. There's no time, bro. Where's my hand, for fuck's sake? What the hell is this, damn it? The only sample. It's not here. What's all that noise over there? Hey, what are you doing with my hand? Ugh, fuck.
Pervert. Dmitry Pavlovich, I wanted to play a little with a stranger. Crap.
Fuck perverts. Hello, gentlemen. Welcome to the DP Lab channel. Today's video will be about bionic prosthetics. I've wanted to work on them for a long time. I haven't told you about this before, but now everything is at the pre-release stage, and soon I'll be testing it on myself. Well, let's see what we've achieved. So, gentlemen, what can I tell you? About 2.5 years ago, I filmed my first video, and it was about bionic prosthetics. Since then, I've gradually learned all their various pros and cons, and over time, I have bought an insane number of all kinds of prosthetics, both expensive and cheap ones, trying out different types and brands. Through this process, I realized, at least based on my own personal experience, so it's a subjective opinion, that the way I use prosthetics is not at all how most people typically use them. That's the impression I got. And I decided to start making my own prosthetics. Well, first of all, I wanted to help other amputees because the price for Autobook is sky high. And many prosthetics are very flimsy. So when you do any kind of sports or real work, they just fall apart completely. Roughly speaking, if you take this Autobock prosthesis, well, for now, on the one hand, it seems like there are no particular difficulties, but actually there are quite a lot of important things to consider. In fact, there are numerous aspects and details that need to be kept in mind. There's not much space, and we need to achieve high torque and decent speed. Like how this opens and closes. If it's a bit slower, it might still make sense, but we really want to make it better than the competitors. Then there's the weight. Yeah, a heavy weight is also a big problem here. And one of our main problems that we are currently facing is the gears, because if some things are ordered from China, remember we got those raw gears and they just wear out. If you try to get something custom made here, they want ridiculous amounts of money and the lead times are just unreasonable. So basically, we had to learn how to do it ourselves. You saw in the previous video that awesome gear hobbing machine from 1941. That's the one we used, right? Yeah, that's the one we used to make the gears. Let me just say that as for... Actually, we'll show you now. The gears turned out really precise and they run very smoothly. And I also want to mention these gears generate a decent amount of torque. As for the engine itself, we've tried a lot of things. We've looked at a lot of options. In short, the motor with the gearbox is made in China. That's all I can tell you about it, because no one helped me, no one gave me any tips, everyone kept everything secret. It was a whole process, but we found our own...
I'll explain a bit.
How it was done. Yeah. A bit later, we'll talk about the motor and the gears. I think we found the perfect match. So it's up to 12 volts, and as I understand it, it's a two-stage planetary gearbox.
A planetary gearbox, yes.
Yes, it's very high quality, and it's not cheap, even for something made in China. Do you remember how much it costs? 26,000 rubles for one. But if you take those, I don't remember who made them for Autobock, some Germans, right?
Autobock is made by Vollhaber, but those are Germans, and European supplies are...
Yeah, and I don't think the price is exactly cheap either. And often...
They actually don't even list the price for customers in Russia, not at all.
So roughly speaking, here's what else we've done. Well, aside from all the mechanics themselves, Gleb will talk about that in more detail in a moment. Yeah, this is what it all looks like. There. So what do we have here? D16, right? On these
samples.
D16T engine and WT20V or WT6 Titan.
WT6
Titan. We'll have two samples, well, two product lines, basically. One is reinforced specifically for sports, and the other is intended for everyday use. The reinforced sports version will be milled from durable titanium, and later, for the regular prosthesis, I think the fingers will probably be made by a process called pressure casting. I think that's the direction we'll go. For now, you can mill them.
We're still considering different options.
Ideally, pressure casting would be great. It's unclear what the strength would be.
Ideally, we need to achieve consistently exceptional quality with high productivity, because the volumes we want to reach, of course, imply...
Just imagine how many milling machines we'd have to set up.
That would actually be economically unfeasible.
But for expensive sports prosthetics, I honestly think that VT-6 titanium is absolutely perfect for this purpose. There are still some minor issues present everywhere here. since the service life of prosthetics for all competitors is 3 years. That's what's considered, not the warranty period, but the operational lifespan. And with heavy use, well, all the moving parts wear out. We made all our joints with needle bearings, not just simple bronze bushings, but actual real needle bearings. And that's a very important distinction to make. If we take, for example, our so-called Chinese wonder, this particular Chinese wonder right here in front of us, well, how should I put it? Well, this one clearly won't last long. I mean, here it's just bushings. Everything is simply screwed together. It's not focused on that. Oh, is it?
Then it's not focused on that either. Focused.
And you can't really say it's cheap either. So the set, prosthesis, cover, 2 myosensors and charger cost about 120,000 on leak, if I remember correctly. Just so you understand, if you also make a socket for it, the prosthesis will end up costing you around 200,000, but it's basically nothing. Its grip strength is pretty weak, right?
About 5 to 6 kilograms or so.
Well, that's how it is, but still, it works, not like some cheap knockoff for 15 grand. In certain situations, you can use it like that. And most importantly, in our prosthesis, let me show you, this is the electronics. All the electronics are ours too. Mr. German, I'll show you sometime. He's quite a flamboyant guy. Anyway, he developed the board for us. So this is the controller, and the myosensors are connected to it. These are the myosensors we use. And the Chinese manufacture them. You can even try making them yourself. They use a low noise op amp, and basically they convert some kind of signal here into an amplitude signal. And in principle, everything works. Because you know, do you have any idea how much they charge for those things? They cost around 30,000, I think. For 2 pieces. For 2? Yes. That's pretty expensive, especially since there's nothing particularly special about them.
In general, yes, we're working on this as part of the Myo project. So for now, we're using the Chinese ones, but we want to make our own. The only problem there, in my opinion, is making the right contacts. It's silver, coated with silver chloride.
Well, that's not difficult.
The main thing is to make sure the silver chloride adheres well. That's basically how silver chloride electrodes are made. So the technology is known, we just need to try making them, and
maybe with this gas dynamic spraying?
Does it smell like that? Spraying silver chloride onto silver? I'm not so sure about that.
Well, you can use silver chloride with this, well.
It's done electrochemically, like a silver chloride electrode, yeah. So, and
for what purpose? So it doesn't oxidize?
Just so that any metal pressed against the skin turns into a battery.
It's clear.
But here it's already getting in the way.
If you make gold, by the way, yes, in fact, if you make gold-plated contacts.
Maybe?
Yes. Does anyone have an idea about this? Because here, I don't know. At this moment, it won't cost anything to precipitate 10 milligrams. Cost.
This will not be anything?
Well, it's beautiful and soulful.
Noble question of technology.
You could do something with palladium or something else. We can look into what this is related to. But in terms of electronics, they're not complicated. But a company, for example, Motorica, tried to make something of their own because I don't know what works for them. But that's not the main thing. Can you somehow use it as a photo background? It won't shoot in macro. Everything is so good. You'll see there's a transistor assembly there. That's the control driver. It got blown. As always, right before filming, everything went wrong. Well, in general, these boards are debugged. We'll show the software now. There's a lot of settings, a ton of different parameters, because it's not that easy to control. You have to filter out the noise, and then, well, we've implemented proportional control. It's very important that you can squeeze just a little bit. That's really important when you're picking things up. For example, if you pick up a can of water, if you don't control it properly, you'll just crush it. Just like that. And well, so let's move on. What should we move on to? So, ladies and gentlemen, let me introduce you to the head of the Bionic Prosthetics project, Gleb. Before this, Gleb worked with composites, and he continues to do so. You might have seen his remarkable hands in one of our videos. Now he's overcome his shyness in front of the camera, so please give him a warm welcome. He started working on this project about 4 months ago and has achieved truly tremendous results because I actually know a lot about the topic of bionic prosthetics. Before that, I was the one working on and leading this. And since I had very little time, everything was moving along rather slowly. We worked on this for 2 years. Well, what do I mean by moving along slowly? We developed the controller, basically. It's still here, with just some minor changes. That took a lot of time. and a lot of time went into all sorts of testing. Now we know exactly what we need, roughly speaking. Time wasn't really managed, but now everything is moving ahead by leaps and bounds. So in short, please welcome it. All right, let's do this. Now Gleb will talk about the problems with the mechanical part and so on. Go ahead, Maria. Hit us with it.
All right, let me briefly explain in a bit more detail what specific tasks were set for us and how exactly we tried to solve them. From the very beginning, the main task was not only to produce a truly high-quality product, but also to design it in such a way that it would be possible to efficiently manufacture large quantities of this product over the course of an entire year. We were talking about 1,000 units per year, and that's why, basically, from the very start, we developed the design so that it would be technically feasible at our production facility. By the time I started working on this project, there was already a prototype of the prosthesis. Not this one, unfortunately, as we had to take it apart. But of course, it couldn't withstand any real criticism because it had a relatively low-quality drive, terrible and inefficient gears, it operated very noisily and slowly, and the drive was quite weak. So it was decided to start completely from scratch and thoroughly redesign everything from the ground up, making sure that every single aspect and component would be improved and optimized. We began our work by selecting the drive mechanism. Our colleagues from St. Petersburg were a great help to us. We spent quite a long time with them, working out the technical specifications for the Chinese manufacturers. In the end, of course, the drives were made for us by the Chinese, but it was the technical specifications and the selection criteria, the gearbox, which operated properly and reliably in close tandem with the drive. This important work was carried out collaboratively together with our experienced colleagues from St. Petersburg. Overall, I believe this project was very successful. The drives we ordered the first time turned out to be a very good fit for our needs, and at this point, we are not planning to replace anything. There might be some additions or enhancements in the future, but you will probably hear about that later.
Sorry, let me just add one remark. I definitely won't tell you exactly where we sourced our components from. However, similar types of motors, which are equipped with gearboxes, are commonly used in both dental equipment as well as in tattoo machines. So they're really good and high quality. It's just the reduction ratio. It's a brushed motor, but with proper brushes. And the gearbox here is a two-stage planetary type of very high quality. Did you even take it apart?
Or not? For comparison, here's a drive, specifically an example with a gearbox from Abok. And here's our drive. In terms of size, not only are they comparable, they're actually identical in size. The only real difference is the shaft size. But at the same time, the Abok drive delivers 8 kilograms of force at the fingers, while our prosthesis delivers 20 kilograms. So, in fact, the quality of the drive makes a huge difference. And then, well, during the process of selecting the drive, we had already started developing our own gear transmission and the process of carefully calculating the loads involved. We soon realized that not every gear is able to handle such demanding loads, not every metal and not every type of steel. So we decided to design a fully two-stage gear transmission system, meaning there is a first stage drive gear and a second stage drive gear, both working together. And overall, with the motor's gearbox included, we get a gear ratio of about 1,000 to 1. So our reduction is, of course, very significant indeed. After we calculated the gears, it turned out that not all types of steel could handle it. These gears are designed to reliably handle the torque we need for this application. When Dmitry set the task, he initially asked for the force on the fingers to be 1.5 times greater than that of the competitor's design. And moreover, not only did the force applied have to be significantly greater, but the compression speed also had to be 1.5 times considerably higher than that of our Austrian colleagues, not to mention a few Germans, well, Germans in general, in short, our foreign colleagues. We made the gears ourselves, carefully cutting the teeth by hand, and then we started manufacturing the transmission. But of course, this 1941 German machine tool really isn't suitable for these kinds of tasks, and so we ran into some problems. The first gears were produced, but with them, the assembled prosthesis didn't work at all. It would jam in one position and simply wouldn't function at all. For a long time, we couldn't figure out what the problem was, but eventually, after a lot of considerable effort and determination, we solved it, made the gears more precise, and overall, everything came together and started working the way we needed it to. I want to draw the viewers' special attention to how quietly the prosthesis operates. That is, there is absolutely no grinding, no jamming whatsoever in the gear transmission at all. This is actually very important for everyday use because, of course, if the prosthesis is noisy, it can be very distracting.
So, ladies and gentlemen, I'd like to add a remark, like Don Sova says, add it. So let's add a remark about the fact that Gleb, well, really only had a very superficial understanding of gear transmissions. It all seemed much simpler, but when we started to dig deeper, we had to read, for example, literature like this, for instance, and so on and so forth. It turned out to be a whole separate world with its own quirks. Nothing is as simple as it seems, and it's actually much more interesting. There are all sorts of involutes, angles, and so on. In short, we've learned and are still learning a lot of new things. Mikhail has helped a lot. In short, nothing is as simple as it seems. You can make it work, but it'll make a hell of a noise and break down quickly. Or it might not work at all.
Yeah, well, honestly, I did read up and really tried to figure things out as thoroughly as I could, but actually, most of the work was accomplished by the talented and dedicated team I put together. The engineers are currently working on some quite interesting and innovative things too, but they also work closely with us, and I think we've managed to build a truly great and productive partnership.
Yeah, I also wanted to say that it might seem like money can solve everything, that cash always wins over evil, and you can fix anything with it. But when we tried to order gears, it turned out that just like that, no matter how much money you have, without the right connections, the kids simply can't get it done. You can't just walk in and say, oh, here's a lot of money, make it for me. They might say, like, come back later, or actually, we don't know, get lost, we weren't expecting you. In
general, we eventually came to realize that we need to make the gears ourselves. And we even have the machines for that. Watch gear hobbing machines. They are currently, let's say, in the commissioning and setup stage.
Yes, because one of them doesn't have a gear train, and we actually want to install a servo drive instead of the gear train. We'll talk about that later. Anyway, we'll get them tuned up, it just takes time.
Given our production capabilities, we're working in that direction. I hope that very soon we'll be able to overcome significant difficulties and finally start manufacturing all the gears ourselves and at a high quality.
Well, yeah, we won't be doing the heat treatment ourselves. We'll think about outsourcing it in batches because that's a whole separate topic that we still need to get into. I think a lot of people do heat treatment, so it's not a problem to outsource it. Now, about the steel, what are we making out of 30 kilograms again? Yes?
The gear, in the end, is actually made from 30 kilograms of steel, with a rather relatively low level of hardening for this particular type of steel. But the calculations do not lie. Everything works perfectly and handles the torque that we need. Well,
we'll still do a durability test. The controller, I'll need to tell German that we need a firmware like that, clamp release. It needs about, I don't remember exactly, but around 25,000 hours of operation for them.
Yeah, but overall, we're busy right now, and I don't even know if I've told Dima about... Right now, we're actually in the process of writing the internal testing program for our products. Even while we were doing this, we even had to learn a bit about how to operate it.
Oh, yes. Let me tell you about the controls. There's another huge problem with testing this. When German was making the controller, he needed to test it. And it's very difficult. I was surprised that Gleb learned how to control it, that a healthy person could operate this prosthesis. Because he still uses some of his muscles and there's a lot of noise, so you can't just isolate and tense only one muscle. I'm already used to it. And German was really going out of control, so I had to go to him as a test subject. But Gleb more or less learned. He hung it up, as you can clearly see, and now it works just fine.
Yes, actually, Dima was right. It's really very difficult, especially when actually opening the hand, to make sure that no signal goes to the myosensor for closing. But overall, I've kind of gotten the hang of it.
Then, yeah, damn, it's a powerful thing. We also wanted to tell you something else. We want to show you the software we use to set up the modes. For now, it works like this through...
The board is connected to the computer via Bluetooth, which enables wireless communication. And here you can see, for example, how the myosensors function during both compression and release, as well as what signal is being sent to the motor. We have quite a lot of different parameters here that are being monitored. That is, we can set the sensitivity of the myosensors and also set a current limit, which is very important. We can also limit the release and compression by current. We also have some secondary parameters, which are more technical aspects specifically related to the actuator settings, because at the start of movement, the actuator consumes more power than during further operation. All of this is carefully taken into account, but I don't really think it's necessary to explain it in greater detail. In general, the main parameters are sensitivity, so that I or anyone else can get a proper signal from the myosensor.
Yes, and also the proportionality settings.
The proportionality of the hand, meaning I can squeeze hard or softly. I think a bit later we'll show how this works, how the force is measured on the scales, and how our prototype operates.
For now, the sensors are not attached yet at this moment.
The sensors are actually just gently placed against the skin, that's all. You just need to carefully put them in the right spot. This is basically how prosthetists help people with limb amputations. I just poked at random.
And it seems I got it right.
And it seems I got it right? No, but honestly, I was poking around at random for 2 hours. Then I just remembered where to put them.
How do they stay on you?
Oh, just under the sweater. I just press them down with the sleeve, that's all. But for a person with an amputation, it's clear that they always go in the same place because they're fixed in the socket with receivers.
I'll tell you this, it actually took me quite a while to learn how to control the prosthesis, even though at first it just felt like a stick to me. And for about 3 days, all I did was go there and open and close it, open and close it. But I'll also say this, a lot of people who use prosthetics don't wear them all the time, unlike me. For me, it's like my own hand. I feel bad without it. It's become a part of my body structure, so to speak. I actually recommend to everyone who faces a similar problem to only take it off at night if possible, and to wear it as much as possible during the day. Then at some point, you'll wake up one morning, and it will just click for you. You'll feel like it's your own hand, and life will shine with new colors, so to speak. That's how it is.
Let me also talk a bit about our future plans.
They're not, well, let's talk about you. It seemed to me this wasn't a problem, but for you, the big problem is the shells.
Yes, that's exactly what I wanted to say. For now, our current plan is to make gloves that will cover the mechanical part. This has actually turned out to be quite a serious problem, and a rather complex one as well. Selecting the right and most suitable material is practically a research project in itself. There are thousands of different types of polyurethanes and thousands of different kinds of silicones. Some are very slippery, while others are not.
Yes, let me mention one problem and why. Here is the inner glove covering the mechanism. It's like a filler. That's still manageable, meaning, roughly speaking, it's more or less clear what needs to be done and you can select something suitable. But the outer shell, just so you understand, the outer shell for this one, I don't know, at Tabokovskaya, it costs about 30,000 rubles now. But that's just an unreal price because they often don't even last a month if you use them actively. And look, I tried ordering them here. I don't remember exactly where. We have a prosthetics company here, and it's not bad, but the problem is that they're made from this kind of polyurethane. Here they are, for example. Well, they look pretty good. Not bad, yeah. Yeah, they look good, but it catches on clothing. This part is smooth, but this one snags. And to put on a jacket or sweater with this kind of glove, you have to put on some kind of plastic bag and shove your arm in. It's a very frictional material, you know. Well, it already costs 5,000 rubles. But the point is, they're much lower quality. I've tried it. Another problem is that polyurethane stiffens in the cold. Even the big prosthesis jams up and stops working. I tried to make a silicone one for the cold, but with the silicone one, you have the same problem. You can't put anything on. And we also had this other thing. So what about the ones from the Chinese? Can you show the Chinese glove? No, the one that was all slimy. You don't have it right now? The one that looked like a condom? No. I still have some Chinese gloves. They're all slimy like that. And we started thinking about how to make them, what technology to use. And I had a question. How do they make them? If you look closely, you can see all the folds and so on. I thought, do they really mill the mold like that? And then we saw a callus on the Chinese gloves. Right on it, and we realized that it was a human hand, an imprint taken from it. We started experimenting, and I also looked into it. We really liked the Pakistani methods of casting these plastics. Remember, actually, I saw dolls too. That was another idea. You make a mold, pour polyurethane into it, you put it in hot water, part of the polyurethane sets, the rest just pours out. So basically, that's the process. The Pakistanis outsource it to contract manufacturing. In general, that's what we're working on right now. Yes, we already have some...
We're actively working on it, and strangely enough, we got help from some individuals in St. Petersburg. Oddly enough, it was the St. Petersburg individuals who do makeup for filmmakers. They told us a lot of useful and interesting things. In fact, they explained how to do it without using a human hand. Basically, sculptors can just sit down and carefully make it themselves.
But we'd rather just get a cool guy for the job.
They explained how to correctly and thoroughly make casts from a human hand, and we're trying out the technique now. Honestly, it's hard to find the right material, and while the overall process is clear, we're still experimenting with the materials.
If any of you gentlemen work with polyurethanes and can give us some advice, we would be extremely grateful. We're even willing to pay for a consultation. Yes?
Right now, everyone we talk to about material supplies unanimously says that there's currently a significant problem with flexible, elastic polyurethanes in Russia because some components are no longer being supplied to us. Maybe someone really is importing them.
Yes, the main thing is that it should be elastic enough and, most importantly, slippery, so that it slides properly. Well, we'll figure this out, I think. If you ladies and gentlemen are interested, there will be separate videos on this topic. Well, let's demonstrate how our miracle works on the scales.
Yes, let's do it.
Oh, and by the way, right now, since we'll need to do a lot of tests, we decided to try making the sockets ourselves because it's a hassle to bother the prosthetist and keep going back and forth to him. I think in the next videos, you'll see us try to make a copy so that we can... Because I wanted to mention that the socket isn't an exact copy of your arm on the inside. There have to be gaps. That's where the prosthetist's expertise comes in. He knows where to trim, where to adjust things. If you make it exactly one-to-one, you won't be able to do anything with it.
Yes, but the second socket, using the one we already have...
Yes, we'll make it with strength in mind. And in the next video, we'll show you how we're going to figure it out for him.
So many things are generally well-known and clear.
Yeah, exactly. That's precisely what I wanted to say. Right now, we don't have a socket available since I'm currently the only one here, and we don't have a foot either, so we'll have to test it on me for the time being. For now, Gleb is the one who is testing it. Let's show how you manage with the weights, Maria. Let him try it. Yes, this is Mikhail. You've already seen him in previous videos, as you probably remember. A man who is well known in certain circles. Actually, when it comes to concrete work, he never specifically or explicitly claimed to be a concrete worker. He just said, "Who here is the concrete worker?" No one? Then you will be. That's how it happened. You know how they say your initiative can come back to bite you a little. But we like that, so basically we're working in that direction. So yeah. Mikhail will now tell you about the difficulties of making gears, especially in our country, for prosthetics. What challenges there were and so on. And what prospects we have, so to speak.
We ran into the issue that small gears on the scale of watch mechanisms, which are needed for prosthetics, very few people agree to make them with large modules. A lot of people make large gears, but when it comes to small ones, they don't want to. We also ran into a certain difficulty ourselves on our end. We have a machine from 1941, a Reinker, and its minimum gear diameter is, I think, 12 millimeters, either 12 or 16 millimeters. But we needed to make a gear about 6 millimeters in diameter. Because of this, there were also certain difficulties. The machine spindle couldn't get close enough to the table. We had to, file down the machine bed a bit, use different tooling, and raise it very high above the table. There were a lot of such difficulties. We bought a Japanese machine, a Hamai 102 watchmaker's machine, specifically for making very small and fine pitch gears. But unfortunately, we bought two machines, one gear shaping machine for bevel gears. And without realizing it, we only later found out that we didn't get the gear train for the Hamai. So honestly, we're too lazy to make the gear train ourselves. We just don't feel like it.
Main thing is there are already, what do you call them? The fitting, there is...
Some special one, the fitting is splined.
No, but making splines is fine for us.
Splines, yeah, in Morocco it's a whole thing. We decided to install, since we're making our own CNC system, to use a part of that CNC as a proper dividing gearbox for this Hamai. So the plan is to finish it by January, or at least try to. And
by the way, you mentioned accuracy. Will it work? Will this server be suitable? What kind of accuracy does it need? In the
fourth decimal place, the error in division should not be greater than a certain amount. So the division that is performed there is also quite specific. It shouldn't just be with a remainder, but as Zhenya said, it's a kind of dumb division. I forgot the exact term for it. In the process, you divide with a remainder, but on the next round, you divide again, and this remainder is neither added nor removed.
So that basically the error doesn't accumulate with each rotation. It doesn't build up, right? That's why, as you understand, even now most gear hobbing machines are still mechanical, because the accuracy is just there. The backlash is compensated for, and they work. If
it's strange, a gear with 61 teeth, the base machine's coefficient is 12, and the difference already comes down to the fourth or fifth decimal place when you're carefully selecting gears from the dividing box.
Honestly, I still don't understand how to select them. It seems to me you'd have to sit there for 2 days, swapping this gear train from one setup to another. Just so you understand, let's call it a gear hobbing machine. How much did you say? Maybe a ton of these gears comes with the set. But there are CNC machines like the ones we want to make. So is this possible?
It is possible, yes. Modern machines already come with CNC. The setup is much simpler. Yes.
We just take it and basically do whatever is needed.
You just set the division relative to the spindle, and the servo simply rotates it.
Yeah, and the machine itself isn't worn out, it's in good condition, right? No.
Machine good.
It's from 65. No.
It's from 41.
No, yours is from 41. What about the Hamai one?
65 or 66, I don't remember. Well, it's also pretty old, but it's not worn out. It's a watchmaker's machine, and they usually take good care of everything.
Maybe even the Germans, if possible, with the Hamai. Maybe the Germans converted it to CNC. It will have a new life in your life. Well,
it's big. It can handle gears up to 600.
It'll have a new life. It'll keep working until 2041. 100 years in operation. Once it was making something for the Third Reich, now it'll be making a prosthesis. Yeah.
Everything as it should be.
Well, thanks, Mikhail. That's all. See you. Gentlemen, let's show how the Abokovsky prosthesis grips. We'll set up a proper test stand for grip strength later on, but for now, these are just ordinary scales for weighing Freon. So look, here's my hand, and I'm grabbing it. How much is that? Well, that's 10 kilograms. Let me hold it steady for a moment. Well, it's not too hard to squeeze it all the way. 8. Well, 9 kilograms. It's actually applying pressure to 9 kilograms with just the fingers. Now, if I try with my own hand, with my manly grip, let's see just how much I can squeeze. All right, 22 kilograms. That's me using all my fingers. 22. Now try with this one. It hurts me. And with just 3 fingers, it's a quite pitiful 12 kilograms. No, really, I'm actually using just 3 fingers here.
Not with the whole hand, but still 22.
Now, if you try with 3 fingers, wait, it hurts. 15 kilograms already. My hand is freaking out.
I'm a peasant from Divinyansk. My fingers are like this, so he can do it.
17 is actually a lie. And when you count using the whole hand, the correct number you get is in fact 15.
To be completely honest with you, I am telling the absolute truth.
15. Don't summon the Kraken.
17 and now 18.
With fresh batteries, you can almost get to 20, but honestly, I'll tell you this, it's really, really strong. I definitely wouldn't let anyone pinch me anymore, not at all.
I personally tried this on myself, but you end up with bruises.
Try grabbing me like this. Won't I freak out? It grabs really hard. Okay, go ahead. Yeah, it's true. Girls are delicate. It'll leave bruises. Yes, girls are delicate, but women, bruises. That's exactly what needed to be proven.
Yeah, but overall, let's also take a moment to evaluate and compare the speed of operation. Let's open them up so it's about the same.
Yeah, like this, exactly.
Go ahead.
1, 2, 3. No, wait, let me count. Carefully, we need a stopwatch. Sit down, give it some gas. 2 seconds. Where is it at?
The speed of operation is comparable, but we need to measure it precisely.
In short, I'm completely and totally satisfied. The main thing, of course, is the power, which is really impressive. But I'll still have to add something because it's dangerous. You might accidentally grab onto something you shouldn't and not be able to let go. I need to add a flow limiter and some kind of overdrive mode. If you need it, you just turn it on to full power from your phone. Or if you activate both myosensors twice, it switches to another mode. That kind of compression is still dangerous. What if I clamp myself?
Yeah, honestly, I really think it's actually a bit much for everyday use because, for example, it can easily press in a closed can of Coke with just the thumb, even without wearing a glove.
Yeah. Yeah, I had an incident with the prosthesis, so I have to be careful when taking things out. My younger daughter is 3 years old. She's afraid of heights, but she doesn't back down. She faces her fears and goes down the slide. I tell her, Vika, sweetheart, I'm down here. I'll catch you. Don't you trust your dad? As she was coming down, I realized I had forgotten I was wearing a prosthesis, and there was no way I could catch her gently. I would just bump her. So basically, I made the only right decision. I raised my hands up. And Vika thought trusting dad is kind of weird. But then she got over it and was fine. So don't undermine your children's trust. Use your head. I would have just smacked her hard with my hand. That's what would have happened. That's how it was. It looked spectacular. It really did look spectacular. I totally undermined her trust. So folks, I hope you enjoyed everything. Feel free to ask questions in the comments. We always welcome reasonable comments and constructive criticism. Just don't write crap like, we could have done better. What the hell is this? Well, that's kind of the mark, so to speak, of not very smart people. If you think we're doing something wrong, let us know. We take criticism, both positive and negative, seriously. If anyone has the opportunity to help us out, especially with polyurethanes and so on, or give us some advice, we'd really appreciate it. That's it. When are we going to release? What do you think? When will we finally start?
Right now, our current plans include conducting internal durability tests for the gear transmissions, for the overall mechanical systems, and also for selecting the most appropriate batteries. Actually, I have some thoughts about this in the designers, the electronics engineers, basically everyone involved has thoughts on this, and we've all agreed that, of course, the device should be charged via Type-C. You just take the cable out of your phone, plug it into your hand, and everything should work. I mean, we're almost in 2024. There's no need to stick some Tesla charger into your hand. That's just nonsense. You can
think of it that way.
We'll select the right batteries, set up the electronics, implement all the necessary limits and settings so that everything works properly, and then we'll run internal tests. And overall, when we carefully take into account everything that has been mentioned above, we are now ready to launch a small initial batch, and then, if all goes well, scale up to a much larger production run. However, it will all depend on whether or not we need to make any significant changes to the design. It seems like all the issues are already known, we've taken them into account, and have already addressed them. And at this point, it's truly actually ready. 90% of the revisions from the first version have already been made, and when we launch the small batch, not if but when, we will take them into account. They definitely won't affect functionality. They'll mostly impact the manufacturability of the assembly, because at this scale, like 1,000 units per year, which, just so people understand, is 5 per day, manufacturability becomes the top priority. You really have to sit down and just keep making them constantly.
I wanted to say I think we'll run some tests, make a couple of sockets, maybe a couple of prostheses, and I'll go to Priskovy or Evergak. The toughest test of all is riding a mountain snowmobile. If it can withstand all that, especially in sub-zero temperatures, we also need to pick the right lubricant, otherwise it gets too thick. Yes?
As for the lubricant, I do have some thoughts in general. We're obviously working on that issue too, I just haven't mentioned it because it's already
such a fine detail, because usually my prosthetics wouldn't last even 3 days of riding. Even this one, for some reason, had a crazy amount of play, remember? Yeah,
I replaced the bushings, rebushed everything, and rethreaded all of the holes. Well, yeah, that's actually true.
Well, we'll see what happens. I think, honestly, there's a really good and promising future ahead for this. And also, in the future, we're going to do neocortex integration. I want to make a prosthetic with feedback. Gentlemen, let me share a thought right now. What do you think about this? You know, I'm telling you, I have a chip implanted in my hand, right? Dangerous Things, that's the company that made them. They also sell these products in America, specifically small, sterile neodymium magnets. They're extremely minuscule, often, oh God, the Paparnish channel, I don't remember. The guy worked with Karyos, and for some reason they called him a gypsy, though he hardly looked like one. Sorry if I offended anyone. He was sticking those tiny neodymium magnets into his fingers. But for what purpose? What happens is, if you try to feel an alternating current, you start to sense it. It vibrates and presses on the nerves. So I decided to order some neodymium magnets for myself to implant them in the muscle on this side and that side, and to put coils in the prosthesis. For what purpose? We install a position sensor, basically just put an encoder on the motor, and strain gauges that are positioned in the hand. So the main idea is to create something like proprioception, the sense of joint position in space. So when the joint is open, I get vibration with a certain amplitude on one side. When I squeeze, it shifts from one side to the other. And the human brain is such a thing that if you give it feedback, over time it builds a body schema. And you'll start to perceive it as your own sensations. And you can also add a third one to the strain gauge. The harder you press, the stronger the intensity of the vibration. I think everything should work with this kind of technology. This would be a real breakthrough, because having feedback and at least some degree of sensitivity would be really great. Otherwise, you still have to look visually to check as before. Sometimes I can feel the hardness of a surface through the vibrations in the stump. Well, anyway, we need to experiment. Maybe we'll invent something new. Well,
Actually, Dima shared this idea with me quite a while ago, about a month and a half or 2 months back. We already have a ready-made solution for this task. We just haven't implemented it in the current prototypes yet, but overall we're currently working on it too.
well then, gentlemen, all the best. Subscribe to the channel, give us a like. Yes,